All right, so a few more solve trig equations. We'll use all the same algebraic tools we used in the last lesson, but we're going to add a few trig manipulations or trig identities in to solve the rest. So go right into an example. Find all the solutions of sine squared x minus sine x plus 1 equals cos squared x. All right, and we want to find these on the interval between and including 0 and 2 pi, but not including 2 pi. So we don't have to get multiples of our solutions. So first thing we want to do is kind of stand back and have a look and notice that I'm in cos squared and sine squared and 2. I could factor this side, but this side would give me a little bit of trouble. So the first thing I want to do is go ahead and get my cos squared onto the other side. So I'm going to take sine squared x minus sine x plus 1, and I'm going to subtract cos squared of x. So now that all equals 0. And then I think I'm going to use a trig identity for cos squared, and then I'll be able to combine terms because I'm going to get a function, I'm going to get sine squareds instead of cos squareds. So remember the Pythagorean identity, cos squared of x plus sine squared of x equals 1. So if I'm substituting in for cos squared, then I'm just going to subtract sine squared x to the other side. So let's do that. Sine squared x minus sine x plus 1 minus 1 minus sine squared x. I'm going to skip a little bit of a step, right? I'm going to turn this into a plus. Well, no, I won't. 1 minus sine squared x equals 0. All right, so now I can turn this into a plus by changing the signs inside, and now I can disregard the parentheses and combine terms. So I have sine squared plus sine squared is 2 sine squareds of x minus sine x, and I have a plus 1 minus 1. That disappears, and so I have equals 0. That got really pretty really fast. Factor out 1 sine x, and then zero product property. We're looking for angles of x where sine x equals 0. That's easy enough. And we're looking for angles of x where 2 sine x, we're looking for angles x where 2 sine x minus 1 equals 0. So this one I just need to solve a little bit. Add 1, divide by 2. Okay, now I'm going to use the unit circle. I could use left-hand rule, but I don't think I really need it. We want to find sine x equals 0. Sine means there's no elevation, or sine is all about y, and there's no elevation on y. So we're looking at 0 and pi. So at 0 and pi, angles of x, sine x equals 0. On the other condition, sine x has to equal 1/2. Well, that's the low elevation because y is the smaller of 1/2 and root 3 over 2. So that's at pi over 6 and at 5 pi over 6. Since this is positive, I have to do all students take calculus. Sine x would be negative in this region and negative in this region. So I want positive values. So I'm looking at these angles. So I can write my whole problem out. This condition is true for x equals 0 and pi, and this condition is true for x equals pi over 6 and 5 pi over 6. And so now I'm going to write my answer all pretty. All the x values, all of the angles that make this sentence true on this interval are 0, pi over 6, 5 pi over 6, and pi. I don't know if you've noticed, but all my examples seem to have pi over 6 as the reference angle. That's not on purpose. I'm just picking examples from the book kind of randomly. All right, so find all solutions of sine x minus cos x equals 1. On the interval, including 0 to 2 pi, not including 2 pi. All right, so in this case, we'd be happy if we could convert this somehow, if we had a sine squared and a cos squared, or even just one of them squared, so I could use the Pythagorean identity in order to turn the function into all cosines or all sines. So I could trade out a cos squared for a function of, or an expression of sine squareds, but I don't have anything squared here. Luckily, I know how to do that. If I square both sides of this equation, I get sine x minus cos x squared still equals 1. Well, this would be 2. No, it wouldn't. Just making that up. Sorry. This would be sine squared of x minus 2 sine cos x minus or plus cos squared x equals 1. So just so I can make sure that I didn't lose you, I don't think I did, but just in case, let's say sine x is a and cos x is b. And so we're really just looking at the square of binomials, where it's the first number squared minus 2 times the first times the second plus the second squared. That's all I've done here. But now we are working with sine squareds and cos squareds that I can kind of play around with. Sadly, though, I haven't come up with anything better. I can change this cos squared to end up with sine squareds, but I'm still going to be stuck with this cos x. In fact, this was just a tragic error. It's a common error and a mistake that I made. I would have erased it and retaped the video, but this is going to be a short enough video, and I thought it would be useful to show that often you will make a move and realize that you've made the wrong move and you just have to back up. So I'm actually going to back everything up and do something different. I'm still going to use this, so I'm going to keep that, but I want to put my sine x on opposite sides of my cosine x. So I'm going to add cos x to both sides. Still want to do the same thing I was talking about before. I want to end up with squares because those help me. Having trig identities I can work with, but I want to get my sines and my cosines on the opposite side. So on this side I have a sine squared of x, and on this side, using the exact same distribution, I have 1 plus 2 cos x plus cos squared of x. So now I want to just turn this side into cosines of x's, and I can because I have a sine squared. So first let's subtract it onto the other side because I want everything to be equal to 0, and I'm going to rearrange. So I have cos squared x on this side, and then plus 2 cos x plus 1. I'm going to subtract the sine x to the other side, but I'm also going to convert it, right? I want to use the Pythagorean identity, sine squared of x plus cos squared of x equals 1, and I'm going to convert sine into coses, so I'm going to subtract cos squared of x. And when I do that, I get minus 1 minus cos squared of x equals 0, and now combine everything. So a cos and a cos is 2 cos squared x's, plus I have 2 cos x's, and 1 minus 1, 0, so that equals 0. I'm going to factor out 2 cos x, and I get a cos squared, or excuse me, a cos x plus 1 equals 0. 0 product property, 2 cos x equals 0, and cos x plus 1 equals 0. Cos x equals 0, divide by 2, and cos x equals -1. Okay, let's see what we have. Unit circle again. Cos x's equals 0. We have no elevation or no movement on the x-axis at pi over 2 and 3 pi over 2. And then cos x equals -1 only at pi. So cos x equals 0 at x equals pi over 2 and not negative, 3 pi over 2. And cos x equals -1 at x equals pi. Now, normally, we would call it a day and we'd clean it up and give our values, and technically, we should always check the solution that we get back in the original, but in the real world, we often don't. But whenever we square both sides, it's possible to get erroneous results. Just like squaring both sides in a polynomial, you can end up with erroneous results. So we're going to check our values in the original just to be sure. So the first check will be at pi over 2. So sine of pi over 2 minus the cosine of pi over 2 equals 1. And we're not sure, so we're going to check it. Well, the sine of pi over 2 equals 1 minus the cosine of pi over 2 equals 0 equals 1. That's true, so we know that one is a solution. Same thing, sine of 3 pi over 2 minus the cosine of 3 pi over 2 equals 1. Well, the sine of 3 pi over 2, that's down here, so the sine equals -1 minus the cosine of 3 pi over 2 is 0 equals 1. -1 equals 1. This is an erroneous result. Last check, sine of pi minus the cos of pi equals 1. Sine of pi is 0 minus the cosine of pi, which is -1. So 1 equals 1, and we're good to go. Now I can clean it up and give my final answers. Therefore, x equals pi over 2 and pi. So while we don't often check our answers always, even though technically we kind of should check our answers always, in some situations you have to always check. So just like in polynomials, there are extraneous solutions often occurring under certain operations. The same thing is true with trig functions, and they carry forward from polynomials. So when you square both sides, because the act of squaring can change positive and negatives up in a way that you can get extraneous results, you have to be sure to go ahead and check your solutions whenever you do that operation for sure. That's it. The end of solving trig equations.